If the ball has an initial velocity of 25 meters per second and is launched at an angle of 50 degrees above the horizontal, determine the ball's time of flight, its range, and its final velocity just before it hits the ground. Now, whenever we have done any of these types of questions, the very first thing that we've always done is what? Look back at your previous examples and tell me what we always do first, regardless of what the question reads. Anna.
We determine the x and y velocity.
Good. Determine the x and y components of the initial velocity. So let's take a look at our initial velocity. Our initial velocity is 25 meters per second. This is it right here. And we want to break it up into corresponding x and y components. The x component is the horizontal component, this part right here. This would be the initial x component. This vertical component represents the initial y component. So this blue line here, the initial x component, represents the adjacent arm of this triangle with respect to the hypotenuse 25 and the angle 50 degrees. So if we are looking at adjacent and hypotenuse, what trig relationship is that? What trig ratio are we looking at? Selena? Adjacent hypotenuse. Think of the term SOHCAHTOA. Exactly. So it's the cos. If we want to determine the initial x component, it's going to equal 25 meters per second times the cos of 50 degrees. Punch this into your calculator and give me the initial x component to 2 sig digs. Good. Plus 16 meters per second. The fact that it is plus, what does that tell us? Alex?
Well, you defined it as it going to the right or east.
So in projectile motion, we say that anything positive is right or up. So since we're talking horizontal, this positive tells us that it's right. Evie?
I get confused. How do you know that it's close? I know the angles, but isn't the x the adjacent because y would be the opposite?
So this line right here, you have to look at each unique triangle as a unique triangle. We have the angle in between, and we're concerned with this length, which is the adjacent arm with respect to this angle. Correct? So this blue line is adjacent to, which means beside, the angle 50 degrees. Whereas this red line, it's not beside the 50, it's actually opposite of the 50. Okay?
If you know already what x is, like, I don't know.
We don't know what x is, we know what the hypotenuse is.
Yeah, but like, if you're finding x, wouldn't the adjacent angle be x? So shouldn't it be OH instead of AE?
Hold on for a second. So we've punched this in and we determined that the x component of the initial velocity is 16 meters per second to the right. Now we have to do the same for the vertical component rather, v initial y. So this red component is the opposite to 50. It's the opposite arm of the triangle with respect to the angle 50. So if we're looking at opposite, and hypotenuse, what trig ratio are we looking at for this? Sine. So in order to determine it, it's going to be 25 meters per second times the sine of 50 degrees. Now here's a little trick. The x and the y are always going to be opposite. So if one is cos, the other one will be sine. If one is sine, the other one will be cos. So you have to know that. So you could have just guessed that since the x was cos, that this y must be sine. All right? If we punch these into our calculator to two significant digits, what do we get? Alex?
19 meters per second.
Positive 19 meters per second. So the initial velocity in the y direction is going up. Okay, we haven't even attempted to answer the question yet. All we've done is determine the initial x and y components of the velocity. And that's what you should do for every projectile motion question. Just determine the initial x and y components. Now let's set out to answer part A. In part A, they want us to find the time of flight. Sometimes when I jump above the ground, I wish I could stay in the air forever. I just feel like flying or floating. But I can't, because something always sends me back down to the ground. What is it? Gravity. Gravity will affect your time of flight. In which direction does gravity work? Vertical or horizontal? Vertical. So when looking for the time of flight, we have to look in the vertical direction and all of the y components or y information. So we have to write down everything we know about the y direction. Well, we just calculated the initial y velocity. VIY is 19 meters per second. What else do we know?
Acceleration is negative 9.8 meters per second squared.
Good. The acceleration is negative 9.8 meters per second squared. Negative implying that the acceleration is down. Now take a look at this diagram for a moment. The golf ball starts here and ends up on the ground. So vertically, its change in position, what will its change in position be before and after? Josh?
Negative 30 meters.
Is the displacement down or up? Does the ball eventually go down or does the ball eventually go up? Down. So we have to account for that and say the displacement is negative 30.0 meters. And they want us to find delta t. That's the whole point. I need an equation that incorporates V1, A, delta D, and delta t. What equation will that be? Alexa?
I have a question first.
Yep.
Do you have to incorporate all of them into it, or could you use, like, for example, the acceleration equation, like v over t? Could you switch that around?
You could, your variables don't have to include everything that's given. However, the acceleration equation cannot be used because the acceleration equation is delta v, which implies that you have both v1 and v2.
Negative 2 VIY over UY
Negative 2,
times.
what equation are you looking at?
Wait, mother equation.
Okay, so we're going to use delta dy is equal to v1y delta t plus 1/2 ay delta t squared. Is that the one that you're using?
Yeah.
Okay. Now, we're using this equation to solve for time. Now, in the past, we got a little nervous because since there are two t variables in this equation, we were hoping that something would simplify out, whether it was v1 that was 0 or if it were delta d was 0, as in a type 2 question. In this case, nothing's going to simplify. If nothing simplifies, what are we forced to use? Good. So we have to use the quadratic equation. And this is what's unique to type 3 questions. Megan.
In type 1, we brought, I don't know what we did with the delta d. I think we brought it over and then we divided each side by delta t.
So that's a type 2 that you're looking at?
You do that.
So in type 2, we did that because delta dy was 0.
Oh, okay.
In this, nothing is 0. So we can't simplify or remove anything. So we have to use the quadratic equation. The only problem is we have to make this look like a quadratic equation. Right now, some of us can't see that this equation is a quadratic equation. So let's sub in what we know. We know that negative 30.0 meters is equal to plus 19 meters per second, delta t, plus 1/2 negative 9.8 meters per second squared times delta t squared. A couple things have to happen in order for this to look like a quadratic equation. Quadratic equations are always set to 0. So the first thing we're going to do is take this negative 30 and bring it over the equal sign. So we have 0 is equal to 30.0 meters plus 19 meters per second delta t. Now, what is 1/2 of negative 9.8? Alex?
4.9.
So it's going to be negative 4.9 meters per second squared delta t squared. Looking more like a quadratic equation. I'm going to just simplify it just a bit more, so this looks more like a quadratic equation. I'm going to get rid of the units, and I'm going to put everything on this side. So I'm going to say negative 4.9 delta t squared plus 19 delta t plus 30.0 equals 0. So this is standard quadratic equation form. Where this term here is our A, this term here is our B, and this term here is our C. Does anyone remember the quadratic equation? Does anyone know the song? If I start singing the song, will you sing along so I don't do this on my own?
Yeah.
Okay. X is equal to negative b plus or minus square root of b squared minus 4ac all over 2a.
That's it?
Yeah.
Oh.
So it's like Pop Goes the Weasel. Get it?
Yeah.
Don't like it? So x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a.
I do an accent.
It was not intentional. So we have to sub this in and we have to get values for x. You should end up with 2 values for x. We're going to dismiss one of them, but you have to figure out which one only after you plug them in. So I'm going to plug them in, and then we'll see what we get. This is really good practice, by the way, because many of us struggle when it comes to computing values of x for the quadratic equation. What I normally do is I normally simplify what's under the square root. If you punch this into your calculator, you should be able to simplify it. When you compute this, you should get 2 values for x, negative 1.2 and 5.1. We're going to reject the negative 1.2 because we don't have negative time, and we're going to accept 5.1 as our time of flight. Therefore, time of flight is 5.1 seconds. If you solve and calculate the time of flight, you have all the information you need to calculate every other variable in these type of questions. Part B, they ask us for the range. How far horizontally the ball will travel. So when you're looking at the range, you're looking in the horizontal or x direction. What do we know about the horizontal and the x direction? Alex?
Alright, so V1x is 16 meters per second. Delta t is 5.1 seconds.
Good. So from there, we need to find delta dx. Every time we've done range so far in the first types of questions, we've used the same equation. It's going to be known as the range equation, even though it's just a modification or a rearrangement of the equation for velocity. So the equation for range, if you look back at the previous lesson, delta dx is equal to the initial velocity times the time of flight. So if we sub this in, (16 meters per second times 5.1 seconds, what do we get for the range of this golf ball? Matthew.
81.6 meters.
So to two significant digits?
82.
Good. Now, when expressing this displacement, what direction would you say? We would say to the right. For part C, we're going to take out a sheet of paper. In this example, they ask us for the final velocity of this projectile. Now, what we need to know about projectiles is the nature of their final velocity. Regardless if you launch something horizontally above the ground, or if you launch something from the ground at an angle, or a combination of the both. If you launch something that is above the ground and at an angle, the characteristics of the final velocity are always like this. Think about how an object travels along a projectile. It always returns in this kind of direction, down on an angle. And this is a result of the fact that it has two components to its velocity, both a horizontal and a vertical. So your job in part C is to determine the final velocity. And you could be asked to do this in a type 1, a type 2, or a type 3. And the steps for all three of these are the same. Your job is to find the magnitude and the direction of this velocity, the projectile just before it hits the ground. So how do we do this? Well, we have to know that this velocity has both a y component, which we will call v final y, and it also has an x component, which we will call v final x. So what we're going to set out to do is determine the magnitude of v final y, the magnitude of v final x, and then use Pythagorean theorem to determine the magnitude of the final velocity. Sound like a plan? So let's do the first part. Let's determine the final y velocity. In order to do so, we have to write down everything we know about the y direction. So we knew that our initial y velocity is positive 19 meters per second. We know that our acceleration in the y direction is negative 9.8 meters per second squared. Our displacement in the y direction is negative 30.0 meters. Our time of flight is 5.1 seconds. And from this, we want to find v final y. Now this is an example like the one that Alexa was alluding to. There are plenty of variables here. There are plenty of equations that we can use to find final velocity. Some of them don't use all of these variables. Whenever I find final velocity, I always go to the simplest equation first and see if I can use it. The simplest equation for final velocity is equation number 2. And equation 2 is v2y is equal to v1y plus ay delta t. This should be your go-to final velocity equation. Use it whenever you can because it's the simplest. So if we plug this in, v1y is positive 19 plus negative 9.8 meters per second squared times 5.1 seconds. Punch this in and report your answer to 2 significant digits. Anybody notice that I interchanged initial final with 1 and 2? It wasn't on purpose, but it actually works out because we need to clarify that initial and 1 are the same and final and 2 are the same. If we punch these in, what do we get for our final y velocity?
Negative 31 meters per second.
Good. Negative 31 meters per second. What does the fact that it is negative tell us?
It's going down.
It's going down. And if we look at our initial drawing, that makes sense. The y component should be in the downward direction. Now, we also have to determine the final x component. I want you to take a look at a quick video. In this video, it shows a projectile. And as the projectile is traveling, you can see the change in the size of the y component of its velocity and the x component of the velocity. So I want you to tell me after watching this video what the final x component of the velocity is. Probably play it twice for you. So we have a projectile being launched, and that's its velocity. But the green is the y component, which decreases as it goes up and increases as it goes down. But what was happening to the x? Well, let's see what was happening to the x. We'll play it again. Pay attention to the x component of this velocity during the entire trip. So the x is the red. What do you notice about the magnitude of the red component of that velocity during the entire time of flight? It's constant. So that is characteristic of projectile motion, and you need to know that and remember that. So the initial x component is constant. So Vix is going to equal V final x. So if we calculated it at the beginning, what was the initial x component to the velocity that we calculated at the beginning? Positive 16 meters per second. Okay, once you've determined the final y and the final x, we're going to use Pythagorean theorem to solve for the final velocity. So we have 31 16, and we want to find this VF. In order to do so, we're going to use Pythagorean theorem, where VF is equal to the square root of 31 squared plus 16 squared. Now, do I have to put the negative in here? Well, I'm looking at the magnitude of this side of the triangle and the magnitude of this side of the triangle. If you actually included the negative, because we're squaring it, it would have got rid of it anyways. But just keep in mind, we're finding the sizes of these, not the direction, just the sizes. So if we calculate this, what is the magnitude of the final velocity? Zeal? So 35 meters per second. That is the magnitude of the final velocity. We're almost done. We have to determine in which direction this is traveling. Because it's velocity, your final answer must include a direction. So we have to find the value of this angle theta. Whenever we've found the angle inside one of these triangles, a right angle triangle, we've always gone to tan theta is equal to opposite over adjacent. In this case, tan theta is equal to 16 over 31. We have to remember how to find theta. So everyone try to get a number on their calculator, a value for the angle. It should not be a decimal number. So this is going to require that you put the inverse tan of 16 over 31. If we do so, what do we get for theta? Yeah, 27 degrees. So we have to report the direction of the final velocity of this projectile. It is 27 degrees, but how do I express that? It is 27 degrees to the right of what? Take a look at this drawing. It's 27 degrees to the right of, what direction is that? Down. So we say 27 degrees to the right of down. There's no indication of if this was happening north or south. Remember that if something's up in the air, that's not north. North is this way, along the different plane. Got it? So this whole page is what you'll be doing whenever you're asked to find the final velocity for a type 1, a type 2, or a type 3 question. We take all of the same steps in order to do so. Remember, final velocities of all projectiles are on an angle downwards. So you have to find the y component, the x component, and the angle. I've given you homework questions. Practice page 78. Practice page 81. And review questions, page 81. These were questions 1 through 8. Make sure all of these are attempted for tomorrow, and I'm going to be taking up some of the more difficult or challenging ones. Be sure to use your solutions manual, and if you like, you can also use the conference on the LMS to discuss amongst your peers possible solutions to anyone's